Good morning to all of you. Let us move to the 12th lesson on conduction, heat transfer through cylinders and spheres with internal heat generation. In the last class we have seen the conduction problems through a slab with internal heat generation, and now we will see in cylinders and spheres. It belongs to one-dimensional steady state heat conduction with internal heat generation. At the end of the session, student will be able to understand what is the governing equation for conduction with internal heat generation under steady state condition, one-dimensional for cylinders and spheres, and how to solve this equation, and how to apply boundary conditions, and what is the temperature profile shape, and how to determine the magnitude, determine the position and magnitude of maximum temperature in a cylinder or sphere with internal heat generation. Let us quickly have a look at cylinder. Imagine this is a pipe without internal heat generation. Before going to the internal heat generation problem, let us understand the temperature distribution in a cylindrical system without internal heat generation. So there is a pipe, the inner radius is R1, Ri, outer radius is Ro. Let the inside temperature is maintained at Ti and outside temperature is at T0. The governing equation, one-dimensional in radial system, is 1 by R d by dr of R dt by dr equal to 0. So 1 by R equal to 0 goes off, d by dr of R dt by dr equal to 0. So if you integrate once, you will get R dt by dr equal to C1. That means dt by dr is C1 by R, and hence T equal to C1 log R plus T2. C2 is the temperature distribution equation in a cylinder without internal heat generation. Because of this logarithmic term, the temperature variation is logarithmic in nature. And to solve this C1 and C2, you need two boundary conditions. One is at R equal to Ri, T is Ti. At R equal to R0, T equal to T0. By substituting this, you will get Ti is equal to C1 log Ri plus C2, T0 equal to C1 plus log R0 plus C2. Subtract one from the other, you will get the C2 cancel, and you will get C1 value Ti minus T0 by logarithm of Ri by R0, and substitute C1 in one of these equations, you will get the C2 value. And hence you can say T equal to, by substituting C1 and C2, Ti minus T0 logarithm of Ri by R0 into log R0 log R plus C2. Multiply this term with minus sign. So first you will get T0 log Ri minus Ti log R0, and that minus sign changes log R0 by Ri as log Ri by R0. So it can be simplified and written as T equal to Ti log R by R0 plus T0 log Ri by R divided by logarithm of Ri by R0. So this gives temperature as a function of radius, logarithmic in nature. And to determine heat transfer, Q equal to minus Ka dt by dr at R equal to Ri. Conduction starts at that point, R equal to Ri. dt by dr at R equal to Ri, substitute that value. You will get Q equal to minus K 2 pi L Ti minus T0 by logarithm of R0 by Ri or Ti minus Ti by 1 by 2 pi KL log R naught by Ri, that is Ti minus Ti by conduction resistance offered per cylinder. So already we have seen this equation for cylinder without internal heat generation. Q equal to delta T by conduction resistance for cylinder is 1 by 2 pi KL log R naught by Ri. Now let us move to the cylindrical system with internal heat generation. Maybe a current carrying wire or a fuel rod in a nuclear reactor. The heat is generated at the center and conducts radially to the outer surface. We have to determine the magnitude of maximum temperature and its position for all practical purposes. Governing equation becomes 1 by R d by dr of R dt by dr plus Q dot by K equal to 0, Q dot. So therefore, you multiply this can be, bring this R to the other side, it becomes d by dr R dt by dr equal to minus Q dot R by K. Now integrate once, you will get R dt by dr equal to minus Q dot R square by 2K plus C1. And again integrate, taking R to the other side, you will get QR by 2K plus C1 by R. You will get T equal to minus Q dot R square by 4K plus C1 log R plus C2. Boundary conditions are same at R equal to Ra, T equal to Ti, and at R equal to R naught, T equal to T naught. So this gives you C1 equal to so and so and C2 equal to so and so. Substituting these in temperature, we will get the temperature distribution equation, and hence you can solve for the temperature distribution. And internal heat generated is given Q dot. So total heat generated is Q dot into volume of the heat generating object. Now suppose there is a solid cylinder like this with internal heat generation. Maybe current is made to pass through the center of a wire, and the surface temperature is maintained at TW, surroundings are at T alpha, and H is the convective heat transfer coefficient. Boundary conditions now become at R equal to R naught, T equal to TW, and because current is made to pass through this, the entire surface is exposed to the environment. So lower temperature will be there at surface and maximum temperature will be at the center. So at R equal to 0, T equal to T maximum, that is dt by dr equal to 0. So using this in the temperature distribution equation, T equal to minus Q dot R square by 4K plus C1 log R plus C2. dt by dr is minus Q dot R by 2K plus C1 by R equal to 0 at R equal to 0. So that leads to C1 equal to 0. And once C1 is 0, T at R equal to R naught is TW. So it becomes Q dot R square R naught square by 4K plus C2, and hence it leaves, this is Q dot and minus, so that leaves C2 equal to TW plus Q dot R naught square by 4K. So the value of C2 is TW plus Q dot R naught square by 4K, and hence you can now write the equation T equal to minus Q dot R square by 4K plus TW plus Q dot R naught square by 4K. And at R equal to R0, T equal to T maximum. So therefore, put R equal to 0, you will get T maximum is TW plus Q dot R naught square by 4K. These are all mathematical integration and substitution. Once you know the fundamental governing equation for the temperature distribution, you can solve it by applying the boundary conditions, and thereafter, if necessary, you can determine the heat transfer rate also. And to determine the surface temperature, TW, again we have to use the conservation principle. Total heat generated within this will reach the surface by means of conduction and enter into the environment by means of convection. So Q dot into volume of this conducting cable pi R naught square into L equal to H into surface area 2 pi R naught L into TW minus T alpha. That will give you TW equal to Q R naught by 2H plus T alpha. Because remember, it is not Q dot, which represents watt per meter cube. So T equal to T alpha plus Q dot R naught by 2L 2H plus Q dot into R naught square minus R square by 4K. R naught square minus R square by 4K. Yeah. So this is the temperature distribution equation. Don't worry, the concept here is don't remember any equation, just go to the problem and then substitute the boundary conditions from the, by solving the general equation you can obtain whatever it may be. So let us not much worry about these mathematical concepts, but the only fundamental thing is we should remember this equation, fundamental equation. This is the governing equation for conduction heat transfer through a cylinder with internal heat generation. Solution of this and substitution of the boundary conditions will lead you to the temperature and unknown parameters in the system. So how to apply that equation we will see with the help of few problems. Consider an electrical wire, maybe of nichrome wire, thermal conductivity 17 watts per meter Kelvin and 3 mm diameter. Thermal conductivity of this is 17, and the resistivity of the wire is given as 100 micro ohm centimeters. Length of the wire is 1 meter, and this is kept in a liquid with the T alpha 120 degrees, experiencing a convective heat transfer coefficient of 4000 watts per meter square Kelvin. You are asked to calculate the surface temperature and the central temperature of the wire. Resistance R for this wire is rho L by conductor cross sectional area, 100 micro 10 power minus 6 centimeters into meters minus 2. So it is 100 into 10 power minus 8. L is 1 meter. Area of cross section pi R naught square, pi into 1.5 in 10 power minus 3 whole square. So 0.1414 ohms. Now heat generated in the wire due to this current passing through it is I square R 200 square into this, so many watts. But whereas in all our derivations we are using Q dot, which is watt per meter cube. So Q dot equal to Q by pi R naught square L, that is, it comes around 8 into 10 to the power 8 watt per meter cube. And the total amount of heat generated is 5658.8 watts at the center. It is a volumetric phenomena, of course. And it reaches the surface and enters from the surface to the environment by means of convection. So the total amount of heat that is generated is equal to heat lost to the environment by convection, and hence 5658.8 equal to H into 2 pi R naught L into Ts minus T alpha. By substituting this, you will get the surface temperature of the wire as 270.1 degrees centigrade. So this now one surface temperature, you got one boundary condition at R equal to R naught, T equal to Ts. And other boundary condition is, because the surface is exposed to the environment, you have lowest temperature on the surface. The maximum temperature will be at the center. So dt by dr equal to 0 at R equal to 0. Anyhow, the governing equation for a cylindrical problem like this with internal heat generation is d square by t by dr square plus 1 by r dt by dr plus q dot by k equal to 0. And the solution is t equal to minus q dot r square by 4k plus c1 log r plus c2. So applying the boundary condition at r equal to 0, dt by dr equal to 0, since the T maximum will be at the center, you will get C1 equal to 0. Now applying the second boundary condition at R equal to R naught, T is the surface temperature or TW 270 degrees centigrade, you will get C2 value as 296.57. So therefore the governing equation, temperature distribution equation is T equal to minus Q dot R square by 4K plus 296.57. So maximum temperature occurs at R equal to 0. By substituting R equal to 0, this term vanishes and T maximum will be equal to 296.57. So the surface temperature is 270, maximum temperature occurs at the center is 296.57. That's all. Next, consider another problem. Imagine a pipe. Thermal conductivity 20 watts per meter Kelvin, 4 mm inside diameter and 6 mm outside diameter, carrying a current of 500 amps. Water at 30 degrees centigrade is circulated inside the tube or the pipe to absorb heat generated, and its outer surface is perfectly insulated. The heat transfer coefficient on water side is 25,000 watt per meter square Kelvin. Estimate the surface temperatures of the tube. Take electrical resistivity of steel, so and so. Now see, the outer surface is insulated and the inner surface is exposed to a convective environment. So obviously the temperature will be maximum at the insulated surface and minimum at this exposed surface. And this pipe wall is subjected to a current flow of 500 amps. So heat generates because this material is offering some resistance for the current flow, and that heat generation being a volumetric phenomena, we represent it Q dot watt per meter cube and Q equal to I square R. This heat generated in this wall can't pass through from the outer surface, so it totally enters into the water by means of convection. And the governing equation for this also d square T by dr square plus 1 by r dt by dr, first term, plus q dot by k equal to 0, and hence T equal to minus q dot r square by 4K plus C1 log R plus C2 is the temperature distribution equation. Solution of this in terms of radius. And now the cross-sectional area for the current to flow is pi into R2 square minus R1 square. Resistivity is given, hence the resistance R is equal to rho 0.08 millimeter square, that is into 10 power minus 6 meter square ohm by meter into 1 by L is 1 meter, let us consider it as 1 meter length, AC pi R square R naught square minus R square into 10 power minus 6 will give you so many ohms. Now Q equal to I square R, which leads to this much, and Q dot is Q by volume of this material pi R naught square minus R square into length of the conductor 1 meter, which will give you 81 megawatts per meter cube. Remember, the temperature distribution equation will give how the temperature is varying in this wall from 2 millimeters to 3 millimeters. Because heat is generated in this material is offering resistance for the current to flow. This material is having thermal conductivity 20. So we are now trying to identify how the temperature is distributed within this wall of the pipe. And that heat generated will enter into this water or the liquid or water at 30 degrees centigrade by means of convection. Now we know the total Q is so many watts, which is equal to entering into the water by means of inner surface HI, AI, TI, T1 minus TI, where T1 is the temperature at the inner phase, TI is the fluid temperature 30 degrees. So that is, by using this equation you will get T1 equal to 34.05 degrees centigrade. So this inner radius or this inner circle is maintained at a temperature of 34.05 degrees centigrade. Now the boundary conditions are at R equal to Ri, T equal to Ti, T1 that is 34.05, and at R equal to R naught, let T equal to T2, that is nothing but T maximum, which indicates dou T by dt by dr equal to 0 or dt by dr equal to 0, which means Q dot R by 2K plus C1 by R equal to 0, which indicates that C1 equal to 0. Dt by dr equal to 0, that is Q dot R by 2K plus C1 by R equal to 0 at R1 equal to 0, and hence C1 equal to Q dot R square by 2K, R at R equal to R naught. We know Q dot, we know R naught square by 2K, you will get 18.22. And at R equal 2 into 10 power minus 3, that is inner radius, T equal to 34.05 degrees centigrade. By substituting that, you will get the value of C2, 155.44. Now the temperature distribution equation is T equal to minus Q dot R square by 4K plus C1 18.23 log R plus C2 155.44. T maximum is at R equal to R naught, that is at 3 into 10 power minus 3. Substituting 3 into 10 power minus 3 in the place of R in the above temperature distribution equation, you will get T maximum is 31.3 degrees centigrade. I think somewhere it has gone wrong. So by substituting R equal to R naught, that is 3 into 10 power minus 3, you are advised to work out for the T maximum value. The T maximum should be more than 34.0. So I think this is not correct. We know Q dot, that is 81.05 10 power 6. R naught is 3 into 10 power minus 3 whole square by 4K. Here itself it's gone wrong here in the calculation of so perhaps C2 may be, so I will leave it to you. And then substituting that here, you will get the T maximum. So please calculate C2 by using this equation and then substituting that value of C2 here, you will get the value of T max. Now let us move to quickly have a look at the sphere with internal heat generation. Imagine there is a hollow sphere of radius, inner radius Ri and outer radius R0. Temperature of the surfaces are T1 and T2. The governing equation for sphere is 1 by R square d by dr of R square dt by dr plus Q dot by K equal to 0. I hope all of you remember the general conduction equation is 1 by R power n d by dr R power n dt by dr plus Q dot by K equal to 0. If you put n equal to 2, it becomes a sphere. So this can be written as d by dr of R square dt by dr minus Q dot R square by K. So integrating once, you will get R square dt by dr equal to minus Q dot R cube by 3K plus C1, and dt by dr is bringing this R square to this side, and you will get the temperature distribution equation as T equal to minus Q dot R square by 6K minus C1 by R plus C2. Again, two unknowns are there, C1 and C2. By applying the boundary conditions at R equal to RA T equal to T1 and at R equal to R naught T equal to T2, you will get T1, T2 by equating them. You will get the temperature distribution equation in a sphere. Let us consider a problem. An 8 centimeter dia orange approximately generates a heat energy of 4.5 into 10 cube watt per meter cube during its ripening process. If the external surface temperature of the orange is 20 degrees centigrade, calculate the temperature at the center of the orange. Take K equal to 0.2 watt per meter Kelvin for the orange. Very interesting practical problem. All vegetables have heat of respiration. So in the process of ripening, they generate some amount of heat energy. It is an internal heat generation problem for a sphere, and the governing equation we have seen T equal to minus Q dot R square by 6K minus C1 by R plus C2. This one, minus Q dot R square by 6K minus C1 by R plus C2. And dt by dr is minus Q dot R by 3K plus C1 by R square. At R equal to 0, at the center, the temperature is maximum, that is dt by dr is 0, and hence C1 becomes 0. Other condition is at R equal to R0, the T is TW given as 20 degrees. So by substituting that, you will get C2 equal to TW plus Q dot R0 square by 6K, that is 20 plus TW is 20 plus 4.5 in 10 cube into 4 into 10 power minus 2 whole square by 6K, 6 into 0.2, that will give you 26 degrees. So the temperature distribution equation for a sphere with internal heat generation is T equal to minus Q dot R square by 6K, C1 is 0 plus 26. Now we know that the temperature at the center is maximum, that is at R equal to 0. By substituting R equal to 0, you will get T equal to 26. So that's all about the internal heat generation problems in cylinders as well as in spheres. So students are advised to remember only the governing equation for one-dimensional conduction with internal heat generation. Except this, don't by heart anything. At any point of time, a problem is asked on internal heat generation, you start with this and solve this. Get the temperature distribution equation. Depending upon the given problem, you apply the boundary condition, maybe in this or in this case. You apply the boundary conditions. By applying the boundary conditions, you can solve for C1 and C2, and then you will get total temperature distribution equation. And at any point within the body, by substituting that R value, you can determine the temperature. Because all these temperatures are having either a logarithm or a reciprocal value, 1 by R, something like that. The temperature distribution with internal heat generation in cylindrical or in spherical systems is hyperbolic in nature. Wherever the surface is insulated like this, heat cannot flow in this direction. The Q value becomes 0. That means dT by dx is 0. Temperature gradient becomes 0, or the temperature reaches its maximum value. So that is what we have to remember. So the governing equation for conduction with internal heat generation for cylinders and spheres we have seen. By substituting n equal to 1, you will get the cylinder equation, and n equal to 2, you will get the sphere equation, like 1 by R d by dr of R dt by dr plus q dot by k equal to 0. The power of R is 1, it is a cylindrical one. 1 by R square d by dr of R square dt by dr plus q dot by k equal to 0, that is for sphere. Integrating it twice, you will get the general conduction heat equation. Boundary conditions, first you have to find the Q value, and since this total heat generated is leaving to the environment by means of convection, you may get the surface temperature as one condition, and maximum temperature position, if you know, at that point the temperature gradient becomes 0, that is the second condition, and applying these two boundary conditions you can solve the temperature distribution. You are getting a logarithmic term or a reciprocal term in terms of radius, so the temperature profile is hyperbolic in nature. The temperature maximum position and maximum temperature can be determined by differentiating the temperature distribution equation. Equating it to 0, you will get the value of R at which the temperature is maximum, and substituting that R, you will get the temperature maximum magnitude of the temperature in the system. So that is what we have seen till now. This covers the one-dimensional conduction heat transfer with and without internal heat generation, and combined conduction and convection through the slabs, cylinders and spheres. And we have only one more application left out on combined conduction and convection, and that we will see in the next class. Thank you very much.